All right, welcome ladies and gentlemen. In this second bonding video, we will be talking about resonance structures, formal charge, and bond order. So you want to make sure you have your notes open. So first up, resonance structures. Sometimes, as we saw yesterday, there are more than one possible valid Lewis structures, and this typically occurs when you have a multiple bond, meaning it can be written in 3 different places. So you'll notice with the nitrate ion up here, there are 3 different locations that we can see that double bond, right? We can put it here, here, or here, because we have 3 oxygens. And resonance describes this possibility, the fact that we have these 3 possible valid Lewis structures, because they're all correct. One isn't more correct than the other. So showing this is literally, when you want to draw Lewis structures, you actually want to draw all of them, and we use this little double arrow to indicate that all structures are valid. Now, with resonance structure, the actual structure of the molecule, what the molecule or the ion actually looks like, it's really an average of all 3 structures. So first of all, I want to point out that these arrows here, they do not mean that a single molecule goes back and forth between the 2. That is not at all what it's saying. It's saying that instead, when you take a population of nitrate ions and you study them under, a lot of scanning electron microscopes and stuff like that, you will see a population of ions that have all of these essentially these possibilities. It's almost impossible to look at just one single molecule. So with resonance structures, we're trying to show with Lewis structures that the real molecule is kind of like all possibilities here. So we show that double bond in multiple locations. Because the thing is, the second point right here, resonance structures can help Lewis structures try to explain observed bond lengths. And what I mean by that is that in the nitrate molecule, it's been found that the nitrogen to oxygen bond is shorter than a single bond, but longer than a double bond. So it's somewhere in between a single and a double bond. Well, we don't have a way of drawing something that's in between a single and a double bond with Lewis structures, but we can show this multiple bond sort of moving to different locations, and that if we take the entire population as an average of all 3, then we have something now, that a way of representing with pen and paper that the observed bond length between nitrogen and oxygen. So with resonance structures, when we have more than one possible Lewis structure, it means that the electrons in the compound, in the molecule, are delocalized, that they can essentially move around, that again, when you take a population of molecules, that the electrons that are in that double bond are kind of found in different locations. So when you're drawing resonance structures, you really want to look for multiple bonds that can be moved around to different locations. So for example, ozone, if we're drawing ozone, drawing the Lewis structure, count your valence electrons, right? 6 valence electrons on oxygen, and there are 3 of them. So our structure needs 18 electrons. So I put the O in the middle and 2 O's on the outside, connect them via a single bond, give an octet to the outermost atoms, count them up, that's 16. I need 18 electrons, so I put a lone pair on the central atom, but this structure is no good because the central atom does not have an octet. So I'm going to take a lone pair from the outside. I'm going to move it to the bond. That way everything does have an octet. So that's my Lewis structure for ozone, but you'll notice that I didn't have to choose the oxygen on the left. I could have chosen the oxygen on the right to get the double bond. So I'm going to draw the resonance structure of ozone. I'm simply going to draw that second possibility. And there is my second possibility, so showing that with resonance structure. So you're looking for, basically, are there different places that you can put the multiple bond, double or triple? Now, formal charge. Formal charge is a way to evaluate Lewis structures, especially if you have resonance structures. So formal charge and resonance structures really do go hand in hand. And formal charge it's a slight calculation. It's the difference between the number of valence electrons that an atom has and the number of electrons you've assigned it in the Lewis structure. So it's valence minus assigned, and it's always that order. So we know how to get valence electrons. That's easy. That's from the periodic table. But the number of assigned electrons, it's all about the Lewis structure that you've drawn. So we have 2 types of electrons in a Lewis structure. We have lone pairs and we have electrons that are in bonds. all of the unshared electrons, i.e. the lone pairs, those get assigned to the atom that they're surrounding. So you have an oxygen that has 2 lone pairs on it, so that's a total of 4 electrons that you would have assigned it. But then we have electrons that are in a bond, and those electrons you split in half. So half the electrons in a bond are assigned to each atom in the bond, meaning if you have a single bond between A and B, A would get assigned 1 electron from that, B would get assigned 1 electron from that. You essentially split all the electrons in the bond in half and give half to one side and half to the other side. So, thing about formal charge, they're not real charges. That's important. So they're not actual charges. What they are is a way to help us figure out which Lewis structure, if you have more than one Lewis structure, represents the most likely bonding scenario for the molecule. Remember, Lewis structures, they're just models. Bonds do not look like lines, and lone pairs do not look like dots. It's a model. It's a way for us to try to represent what's going on. So formal charge is a way for us to evaluate our models, see how close it is to what's actually happening with the molecules. So the most likely bonding scenario will have the smallest possible formal charge on each atom. So 0 is best. So if you have a Lewis structure that has different resonance structures, and you have one where everything has got a formal charge of 0, that's sort of a way of saying that that's the most likely bonding scenario that's happening. If you can't have 0 on everything, then the most likely bonding structure will have the most negative formal charge on the most electronegative atoms. So if you can't have 0 for everything, it's better to have an oxygen with a negative charge on it than a nitrogen with a negative charge on it, because oxygen's more electronegative than nitrogen. So for example, find the formal charges on carbon and nitrogen in the cyanide ion. So it's always valence minus assigned. So valence electrons, carbon has got 4 valence electrons, nitrogen has 5. Now assigning the electrons. Well, carbon, right, this lone pair, that will get completely assigned to that carbon. And then we have this triple bond, and there's a total of 6 electrons in the triple bond. So what we do is we split the triple bond in half, and we give 3 electrons to one side and 3 electrons to the other. So I'm going to assign the carbon a total of 1, 2, and then 3, 4, 5 electrons. And then the nitrogen, likewise, it has the 3 electrons, 1, 2, 3 from the triple bond, but it also gets this lone pair, so 4 and 5. So the nitrogen has 5 electrons assigned to it. So the formal charge on the carbon is -1, which we often represent like this by putting like the formal charge surrounded by a circle around the symbol for the element, and the nitrogen has a formal charge of 0. And you'll notice in this case, if you've done formal charge correctly, that the sum of the formal charges is equal to the overall charge on the species. So -1 plus 0 is equal to the charge on the ion. If it's a compound, then it's going to add to 0. So just a quick example, looking at something with resonance structures, we have carbon dioxide. Now, carbon dioxide has 3 resonance structures. You're only used to one of them, though. This is the one that you're used to. That's the one that you've seen in Regents Chem, right? But the thing is, carbon dioxide has multiple bonds, and those multiple bonds can be moved around because there's we only want, was it 4 plus 12 electrons in it, right? We need 16 electrons in our structure. There's a 16 electrons in this, but who's to say that it can't be like this? Because after all, we still have a total of 4 bonds. Everything has got an octet in this structure. There's still 16 electrons. This is a perfectly valid Lewis structure. There's absolutely nothing wrong. Essentially, I took one of the double bonds from one side and I sort of moved it over to the other side to make a triple bond and a single bond. And likewise, if it's like this, well then who's to say that I can't have the triple bond be on the other side? Right, like that. So here's where formal charge comes in, because we can evaluate these different structures. So valence minus assigned. Oxygen has 6 valence electrons, carbon has 4. So in this case, I've assigned the oxygen 2, 4, 5, 6. I've assigned the carbon 1, 2, 3, 4. And I've assigned this oxygen 2, 4, 5, 6. So in this Lewis structure, everything has a formal charge of 0. That's good. That's considered, that's a likely bonding scenario. In the first one with the triple bond now, again, valence minus assigned. So I've assigned this oxygen 2, 3, 4, 5. I've assigned the carbon 1, 2, 3, 4. And I've assigned this oxygen 2, 4, 6, 7. So now I have a case where I have a +1 formal charge on the oxygen, 0, and then a -1 formal charge on the oxygen. This structure over here that has all zeros is better than this structure, is saying it's more likely than this structure here that doesn't have all zeros. And likewise for this structure, we're going to get, again, a 6 - 7, 4 - 4, and 6 - 5. So now we're going to have the +1 and the -1. Instead of all zeros. So formal charge is a way of saying, yes, we do have 3 possible resonance structures for carbon dioxide, but it's most likely that if you were to find a carbon dioxide molecule, a single molecule in nature, it probably has 2 double bonds rather than a triple and a single. So bond order, final thing in this video. Bond order is actually a fairly simple idea, at least at the depths that we are going in AP Chem. What we need to understand is a fairly superficial idea from this. So bond order, the number of bonding pairs of electrons between 2 atoms, entirely possible for bond order to be fractions. But let's introduce a little bit more first. So for example, between the bond between hydrogen and hydrogen is 1 bond, right? Just 1 bond. So there's 1 bonding pair of electrons. So therefore, the bond order is 1. i.e., if you have a single bond, that's 1 pair of electrons, bond order is 1, right? Single bond, bond order is 1. If you have a double bond, well, that's 2 pairs of electrons, so therefore the bond order is 2. If you have a triple bond, that's 3 pairs of electrons, so therefore the bond order is 3, right? So it's fairly straightforward in that regard, right? Single bond is bond order 1, double bond is 2, triple bond order is 3. And because the length between atoms will decrease as you have more bonds between them, meaning a double bond is shorter than a single bond, a triple bond is shorter than a double bond, as bond order increases, bond length will go down because your atoms are getting brought closer together. But what we're going to do with bond order is more with resonance structures. So we can look at bond order with resonance structures, again, coming back to our nitrates. You know, this is our nitrate molecule. Formal charges are actually shown on it. That's why we see that those negatives and the positives. So if we only look at just 1 bond, this sort of top bond in the nitrate molecule, instead of looking at all 3, notice we have 3 possible Lewis structures. And in the first one, the bond order is 2, right? It's a double bond, so it's 2. But in the second Lewis structure, in the second resonance structure, that same bond, the bond order is 1. And in the third Lewis structure, resonance structure for the nitrate ion, again, that bond order is 1. So we see second order 1 out of the 3 times, and we see first order 2 out of the 3 times. This means that the bond order for that particular bond of the nitrate ion is actually an average of these 3 possibilities. It can be second once, twice, right? Adding up the bond orders, and we divide it by the total number of times when we see it, meaning 3 possible resonance structures. So the bond order for that bond, the average is actually 1.33. It would be incorrect to say that it is second or first, because it's not, because it has 3 possibilities. So we sort of take an average. So that's bond order, and we'll see a problem set dealing with resonance structures, formal charge, and bond order tomorrow.